Hi, my name is Benson Lung, and thank you for joining me for my Chromium University session this afternoon. I'm a developer on the Chromium OS firmware update team, and this talk is an introduction to the new direction of firmware updates on Chromium OS and a beginner's guide to the software pieces necessary to support updates for your peripheral or device on our OS. If you have any questions during my talk, please feel free to follow the link above to our Slido. There will be time for Q&A later. So here's the agenda. We're going to go through why firmware updates, some major challenges that we've noticed along the way, an introduction to LVFS and Fwupd, a description of Fwupd plugin architecture, and a case study of the cros-ec plugin. So to begin with, let's talk about why we need firmware updates. So we tend to think of a device that we can hold as a static thing that never changes. But that actually hasn't been true for decades, to be honest. So devices, both internal inside of our Chromebooks, Chromeboxes, and tablets, and external peripherals, such as USB peripherals, are becoming more complex, and therefore the firmware or low-level software on those devices can be updated. Here are some very common reasons why what someone might update the firmware on a device. Number one, you can fix bugs. Number two, if a security vulnerability is found, you certainly want to be able to update that. And thirdly, you want to be able to deploy new features if the hardware is capable of it, but the first release of the software wasn't. During my career at Google, I've had experience with device firmware updates on Chromium OS going back almost 10 years. I was the kernel developer on the first generation of Chromebooks that used modern multi-touch touchpads and touchscreens. And what I learned was that a bad touch firmware could completely ruin the user's experience with a Chromebook. And we had real situations where we needed to deploy an OTA that upgraded the firmware on a touchpad or a touchscreen to an end user's device. Ever since those early days, touch device firmware has been a qualification requirement for all touch hardware. And updater software along with stable firmware is required to be deployed along with the OS image. The lesson that our team learned was that many devices that we work with have increased in complexity and cannot be simply regarded as static things. So what kind of major challenges do we have for firmware updates? Believe it or not, the number one most common challenge is this, so that Chrome OS is not Windows. So this has happened to us dozens of times. So a partner that we're working with on a piece of hardware may release a new firmware to us to fix a bug that we reported. But literally the software utility that they send us is Windows only. So as a result, we can't deploy the provided utility or the firmware to our customers. And most annoyingly, most of the time, we can't even install it as a developer either. So why does this happen? Well, the truth is that software tools provided by chipset vendors and used to build the firmware for most electronics today are still Windows-based. So naturally, the utility that flashes the firmware to the device is going to be built for Windows. So while most of our vendors' customers are going to run Windows-based PCs, when they're working with us with Chrome OS and Chromium OS, this is a real problem. Again, Chrome OS is not Windows. It's a specialized Linux distribution built by Google. And obviously, we can't run a Windows EXE. We need to look for a solution that works considering our Linux core. So even if you get past that first hurdle, let's say the vendor has written a Linux utility, there's another problem, which is utility duplication. I mentioned before that I worked on touch firmware updates on Chromium OS, and that we require firmware and firmware updaters for each design. Here's an unintended side effect of that. This is a snippet from the e-build of the touchscreen and touchpad updater script package in Chromium OS, which pulls in dependency firmware updater utilities that we built from source. Over the years, Chromium OS has collected 15 of these. Each family of device from a distinct vendor, Synaptics, Wacom, Elan, we have to build a support updater app provided by that company in order to support their own products, but only their own products. So there's a ton of duplication here. Many of these devices are similar, and their update flows are very similar. More on that later. But each vendor writes the whole updater from scratch, and none of the updaters work with each other. And although these utilities are open source, the packages are not likely to be refreshed very often. So as many are built just for Chrome OS, and once we've shipped us an updater to a product that's gone into production, they're not likely to look at the code anymore or give us a new release. Having 15 updaters means it's also hard to audit these for security vulnerabilities and other common bugs. And it's not just touch and touchpad. So Chromium OS has collected a bunch of other updaters too for various internal and external components, many related to video conferencing systems, for example. So this is a real scalability problem too, as each of these packages takes up a little bit of root file system space, and it falls apart when we eventually start talking about hundreds of different models and brands of peripheral devices attached via USB, for example, we may update in the future. The updaters themselves will eventually become a drag on our root file system. We may end up carrying a bunch of extra apps we never use. So from the open source community comes a solution in two related projects. So there's LVFS, or the Linux Vendor Firmware Service, and Fwupd, or the Firmware Update Daemon. So here's a system architecture of LVFS and Fwupd. So LVFS is a web service that provides secure hosting for firmware archives. It's the cloud. Fwupd is the system software that manages the installation of firmware updates. It is client software that is on the user's computer. In this presentation, I'll be telling you more about the Fwupd piece of this architecture with a deep dive into the custom plugins on the left. So the Fwupd project was started 5 years ago by Richard Hughes, a developer at Red Hat. These two projects, LVFS and Fwupd, have had growing support among bigger OEMs lately, from Dell, who uses it to update the BIOS firmware in their laptops that run Linux, and docking station firmwares. Also, HP, Lenovo, and Logitech and others are getting involved as well. So we're just at a tipping point where just enough big industry players are contributing to this that it will soon become ubiquitous. So there's some fundamental advantages to using Fwupd versus the hodgepodge of other solutions. So number one is that it's a common unified utility. So one utility with a common command language and API for all kinds of devices instead of one utility for each device. This solves the duplication issue. Secondly, it works on all common Linux distributions. So not just Chrome OS, but also Ubuntu, Debian, and Fedora. And it is open source. So it's hosted on GitHub, and the maintainers take pull requests from anyone. And it is also well maintained. The updater software itself is in active development with bug fixes and security updates released to all major Linux distributions. Finally, it's expandable and modular through something called plugins. So all of Fwupd is open source, but the part that you'll be most concerned with is its plugins. So Fwupd is architected such that common parts of the firmware update process are in shared code, while hardware-specific parts live in plugins. So plugins are akin to device drivers if you come from a kernel background. A plugin is how Fwupd is able to work with dozens or hundreds of different kinds of hardware. They teach the generic Fwupd project, which works for lots of different hardware, how to support your specific hardware. So in particular, mechanism plugins provide the how. So what hardware skills and software do you need to get started? So this is a list I came up with based on my own experience and a bit of common sense. So number one, you'll need a Linux development environment, a PC or some system running Linux that you can develop on and that allows you to connect to the device you're updating. It doesn't have to be Chromium OS. Fwupd builds and runs on lots of different common Linux distributions. So if you got a Debian, Ubuntu, or Fedora, that's fine too. You have to be comfortable writing in C with glib and gobject familiarity a plus. The Fwupd project is written in C, so make sure that your software engineers are ready for that. And it is open source development is required. So be prepared to provide pull requests to Fwupd's GitHub. So no private code, no drops just for Chrome OS or Chromium OS without going through the maintainers of Fwupd. Any code you write and share must be shared back with them. You want to keep them in the loop as early as possible so that they can steer you back in the right direction if your design has issues. And then obviously you need a target device that you're updating so that can connect to your Linux system running Fwupd. And you'll need two firmware payload versions. So you need two reasonably stable versions of the firmware so you can ping pong back between the two of them to exercise your code. And then finally, you need some kind of reference or guide or existing software. So more on this. So a firmware updater doesn't just get conjured up from nothing. In order to write an updater on the host side, you must have some understanding of the protocol and the API, how the data is moved from the host to the target, and whatever commands you need to get it into the right state. So in terms of the kinds of references or software you might have, I've ranked these from most ideal to least ideal. So the most ideal, number one, is if you actually have access to an existing open source Linux standalone updater. You can build the existing updater from source, you can run it, you can test it on the same system that runs Fwupd. This is great because you can directly compare a working firmware updater with the new one that you're implementing inside of the new project. Since you have the source code, you'll be able to instrument the old code if you have to discover how it works. The second is actually, like I said before, a lot of the partners send us Windows applications. If you have a Windows application, but you have the source code for it, it just doesn't run on Linux, that's still okay too, because at least you have access to the source code for the same kind of code reading. Number three is if you just have documentation but no updater. So this may seem reasonable to have documentation, but source code is always better because if you don't have the source code or an existing app that does the update, you may run into a situation where you think you follow the documentation as best you can, but it fails, and you won't have a working updater to compare against. And finally is the worst case scenario, which is someone's given you a closed updater application with no source code, no documentation, and you're just kind of left to reverse engineer it. It's tricky, not impossible, but hardly recommended. Okay, so I actually wrote a plugin. So I named it cros-ec, and it's currently in Fwupd version 1.5 today. So let me use it as a case study on the process. So let's check in on the developer checklist to see how I did. So the first three I can check off right away. I'm a Chromium OS developer, so I have a full Linux build environment. C code I'm fine with. Open source development, I'm ready to send pull requests to their GitHub. So what about a target device? So I needed a target device to exercise firmware updates, so I picked this one. This is Google's Servo Micro. Servo Micro is a debug board which plugs into a Chromebook and other systems under development. It allows a host system to access our development laptop serial consoles and flash low-level firmware on the Chromebooks externally through this custom header on the right side. It itself is a simple USB device, and it connects to a USB host via a micro USB receptacle. It runs open source firmware, Chromium OS's embedded controller or EC project, and is itself firmware updatable from the USB host side. So target device check. So how about firmware payloads? So for two versions of firmware for this target device, I pulled two recent releases of the Servo Micro firmware from our build system. As I mentioned before, this firmware is open source from our open source EC project. So major releases are publicly posted and available as well, although not many people would know where to find them. Since when you do a public Chromium OS build outside of Google, you still have the necessary packages to flash and program a Servo Micro board. So I can check off the last, that we have two firmwares. So finally, how about a reference? So for building the updater for Servo Micro, I had the most ideal case. So our EC engineers, when they implemented the USB endpoint updater in the EC, they also documented the protocol clearly and wrote a simple Linux updater app, which is also open source and also checked into our repository. The updater is called USB Updater 2, and it's a simple command line utility designed to run on a Linux host PC to update using a USB interface. So here's its usage or help text. It's got a bunch of more advanced functionality, but there are three core things that this reveals about firmware updaters in general. So number one, the utility knows how to talk to the device, and this command reads the device's vital information, usually the device's name and crucially the current active version number on the device. On the host side, the updater app reads the firmware binary image as a file from disk and extracts from it the device name and the version numbers of the firmware in the file. This is called parsing. And finally, number three, the actual command that combines the first two, taking the input file, extracting the actual payload data from it, and then talking to the device to start writing the data out to the transport for it to receive. Again, I have the source code for this utility, so a code reading of these three processes reveals how they're done, and it will be important when we start porting this functionality into its new home, the FWFD plugin. Okay, so it looks like I have all the pieces. Let's go. So here's the phases of development for the plugin that I wrote, and they generally apply to any plugins you might write. Phases 2 and 3, the initial device interrogation and firmware file parser, are actually distinct, or they're not dependent on each other. So you could actually potentially have two different people working on them at the same time in parallel. I did these in series since it was just me doing the work. Okay, so helpful hint number 1. When you're just getting started on an open source project like this, it may be instinct to just avert your eyes to other people's work in the next directory over, especially since they may be competitors or unrelated vendors. However, I would encourage you to take inspiration and copy patterns. If someone, or the maintainer himself, Richard, wrote a plugin in a certain way, then obviously if yours did exactly the same thing to accomplish the same goal in the same style, it would be easier to accept and get merged. So when I wrote cros-ec, I did so after studying some of the other USB device plugins in the codebase above, specifically the Steel Series gaming mouse plugin, which is a very simple which very simply opened the USB device and asks it its version number without doing anything else. And ebit-do, a USB gamepad, which has a full firmware parsing and also write capability, which I use as inspiration for the structure of my changes in phases 3 and 4. So let's talk about the first step in creating a skeleton that doesn't do any work at all, but lays out the files so we can fill them in later. At this stage, what we name the files is important, as is choosing the data type that we use to represent the device. If you examine other plugins, -device.c files are super common, and that's because they are files that are home to the device hardware functions for that plugin. If we dive down into the do nothing skeleton -device.c file from my plugin, you'll see that what will soon become a common pattern. So FWFD is based on G-object, which means that although it's written in C, it is object-oriented, and subclassing is very important to follow. The actual meat of code execution that happens in our plugin happens through vfuncs, provided by classes in FWFD. These are the entry points into your plugin code. In particular, the foo device class provides a vfunc setup, which we are expected to implement. So more on setup later. Okay, so helpful hint number 2, choose your classes carefully. So I mentioned before that FWFD captures a lot of sort of common functionality into its common code. So one of the ways it does this is with subclassing. So cros-ec-usb subclasses FWFD's USB device class. So, and the benefits to this are upper layers handle things like vid-pid matching automatically so that your updater doesn't have to. On device reboot, the upper layers watch for device re-enumeration and reconnection. And it also handles interfaces of devices are helpfully attached to the device's objects. So if your device updates over USB using bulk control or bulk transfers, definitely don't roll your own new class. Subclass is through USB device. Look for other examples of commonality for your device in the FWFD codebase. So one more important thing about the skeleton before we move on is the introduction of the quirk file. So .quirk defines special behavior based on device ID. So quirks are simple key files that allow you to modify device behavior based on ID. It could be used to add extra delay for a particular model of some device which fails otherwise, or set special flags to change update algorithms used. More basically, however, quirks are also how FWFD matches USB devices detected on a system and directs a specific USB device to be attached to the right plugin. In this case, I've added Google's Servo Micro vid-pid and directed to the cros-ec plugin. This also means that this simple text file could be easily expanded upon whenever newer variants of the hardware released with different IDs, without the whole FWFD package needing to be rebuilt. So with the quirk in place in my skeleton driver, skeleton plugin, at this stage, running the FWFD tool does nothing since none of the vfuncs actually do anything but return. But what I should see is that Fwpd at least matches the device's bit PID when attached to my host with the cros-ec plugin. So let's take a look at a basic command that I can run using the old USB-updater2 utility. Using -f, I can query a bunch of the vital information, including its version string. So how can we accomplish the same thing using a plugin? So this phase expands upon the setup function, which previously did nothing. Now it actually needs to serve its purpose to collect information about the device and populate the plugin's data structures so that it's an accurate view of what's going on out there. At this point, we're porting over code sequences from the old updater, as Fwpd plus my new plugin will have to take the same steps to and process the resulting data in the same way. So the most important is the version string, which we want to extract and set as metadata for our representation of the device. So we actually collect a lot more vital information from the device other than the version string, as demonstrated here with the result of this phase of work. The next phase is writing the firmware file parser. So here is again the old utility USB-updater2 with a command that is equivalent to the functionality we need in Fwpd. The file is being read by the utility, and the version string highlighted here is extracted from the file itself and presented to the user. The utility also understands where and how large the various sections are inside of the file. So we've added a couple of new files to our skeleton. The convention is that firmware parsing routines live in files ending with -firmware.c, and that their classes should be fu-firmware or subclasses of fu-firmware. So only one relevant vfunc here for the firmware class, which is parse. This is dependent on how complicated your file format is, but basically parsing is taking the raw bytes from a file and organizing them into Fwpd's fu-firmware image object. And as a bonus point, we can collect and store the version string metadata from the file and staple it onto that object as well, so we can compare version numbers elsewhere. Once the parser is set up, there's a handy Fwpd tool command to exercise it, firmware parse, which will let you point to any bin file, and process it based on a selection. As you can see, this is an output of the parsing work we did with, and note that fu-firmware image objects I mentioned are created and printed here. Step 4. Now we finally get to combine the work we've done in the last 3 phases, culminating in the updater transferring the firmware blob to the device. Again, here's the old USB-updater2 utility running the same thing, deploying a firmware file to the device. For phase 4, we need to implement functions for 2 vfuncs provided by Fwupd device, specifically prepare firmware and write firmware. So these are 2 key functions in this phase, which will stitch together all the work we've done in previous steps. The flow of data through different representations inside of Fwpd is as follows. When you give Fwpd a firmware file and ask it to update a specific device, prepare firmware will take the raw bytes of that file and run it through the parser we built in step 3, which passed back as a firmware object. In write firmware, the handle to the device, representation of hardware, remember, is taken as an argument as well as the same fu-firmware object, which represents the organized data from the file. In write firmware, is where we do all the nitty-gritty device-specific work to put the device into the right mode. Lots of specific porting needs to be put here. That's not likely the same as any other plugin. So please consult your reference code for what to do here. For cros-ec, this required porting big blocks of code. I won't go into in great detail, but you can view the pull request if you're interested. So this is a simple flow diagram of the different entry points that we've implemented and how they connect to each other for a successful firmware write. So now a quick demo of all the functionality I've described so far for the Servo Micro device. So here's my terminal to my Chromebook system with a new version of Fwpd. And I can show you that the first thing to do is just to ask what device is out there. And in this case, you can see that I've identified that there is a Servo Micro Debug board attached, and its version number is 2.4. The next thing I can do is query a file. And let me just, I can parse the file to see what's inside of this file. And I have to give it a firmware type. And you can see that the version number here is higher than the one that's on the device. So what I can now do is I can ask Fwupd tool to perform a write firmware. And there you have it. It updated the firmware, which used to be 2.4 to 2.4.17. And pretty quick too, less than 5 seconds. All right, let's move back to the presentation. Okay, so once I had this thing working at a basic level, now I was able to move on to more advanced features. So one of the most interesting things was that cros-ec-USB devices have dual partitions, read-only and read-write regions, which have independent firmware. It turns out that luckily Fwupd is built with lots of different devices already in mind, and this dual firmware architecture is actually well supported. So we have more vfuncs. I won't get into them in as deep as detail as the others, but there's a detach and then an attach. So the detach puts a device into an update mode, i.e., it reboots into like a bootloader, and the attach gives you a chance to jump back to a runtime mode. And finally, since we have more than one partition, and despite RO being shorthand for read only, we can actually update RO. We can actually loop through the whole process again with a different partition if we set a flag inside of Fwupd inside of our plugin. So this flow diagram puts together all the entry points I've talked to you about up to this point: open, setup, prepare firmware, write firmware, and close, and then inserting the two new optional ones, detach and attach, that bookend write firmware in order to reboot the device into bootloader and then come back. Finally, we add another arrow using the functionality in Fwupd called another write required that allows us to loop around and run the whole thing again, updating the other partition in our device. And as a reminder, I've also put which steps each of these were implemented. And this is actually what's implemented right now in the cros-ec plugin upstream. So in many ways, this flow actually exceeds the functionality of the simple one-shot updater that I started with, USB Updater 2. So for further resources, I encourage you to go to Fwupd's project page on GitHub and all the great documentation they have there. They have a reference manual, they have a plugin tutorial, which this presentation is based on. They have an issue system where you can request features or file bugs. I really hope to see folks who have seen this talk, give a try at contributing to the Fwupd project. It really is an investment in the Linux firmware ecosystem as well as in Chromium OS, and a great way to contribute to a growing open source project that will have real impact in improving security, speed, and simplicity for our users. And also, feel free to contact the maintainers. Richard and Mario are very responsive and very helpful. So with that, I want to thank you for listening to this talk, and I'm ready for Q&A. Have I frozen? Oh, sorry. Okay, so the question is, how does one update the remote side of a potential wireless link? Does the mechanism support this? So in terms of, let's see, how does one update the remote side of a potential wireless link? So the FWFD project is not really, it's not, it's transport agnostic. So as long as there's some underlying, agreement of how the underlying packets are passed back and forth, FWP doesn't really care. So in particular, I've seen cases where Bluetooth peripherals are updated, but the update mechanism is basically just hid, right? So and so just having a wireless device doesn't preclude you from using FWFD. It really depends on what protocols run on top of it. So for example, there is HID support so there's support for updating HID devices in FWFD today. So if a Bluetooth device, for example, supports update via a HID endpoint, there's the fact that it's wireless, there's no physical connection between the two, electrical connection shouldn't get in the way. I hope that answers that question. Okay. So the next question looks like a comment. Thank you. It does. I'm studying Logitech's keyboard implementation. Thank you for your response. Okay. Yeah. It just one extra bit of commentary about Logitech. So Logitech keyboards and mice, many of them actually support multiple protocols. Right? So when you have Logitech in particular, they have a unifying receiver, which is the proprietary wireless dongle. That itself is just a USB device, and I believe that there is support for updating that wireless dongle, which is one end of a wireless link. But from the host perspective, it is just a USB device, just like any just like having my Servo Micro plugged in. So that's a very good question. It is more complex when you start talking about updating the Bluetooth side of it though, which obviously doesn't go through the same path as the connected Logitech unifying receiver. I think we'll give another few minutes for questions, if there are any. Okay, I think if there's no more questions, I can just wrap it up. So yeah, thank you very much for taking the time to watch. And as I said before, I really hope to see more people interested in converting over their updater code to FWFD. And a special thank you to the Chromium University team, which they've done a great job of putting this all together. Anyway, good night. Thank you.